the statement for this problem. Block diagram is given. Position control system. Okay. Okay. And one is coming from here to here. A motor and an amplifier. Feedback within a motor is SKT, and overall the unity feedback in the system. Okay. This particular feedback is a derivative feedback. The first part of this question. In the absence of derivative feedback, that means when SKT is not present or when KT is 0, determine damping ratio when amplifier gain Ka is equal to 5. Then also find steady state error. For unit ramp input. Okay. We will solve this question first. It has got another part also. We will solve that later. So when SKT is 0, that means this particular derivative path will not be there. So in that case, let this be my CS. So CS by RS will be Ka times of S into 0.5S plus 1 upon 1 plus Ka S into 0.5S plus 1. So I'll have it Ka upon 0.5 S square plus S plus Ka. Now Ka is already given equal to 4. So I can substitute this by already given, which is equal to 5. 5 upon 0.5 S square plus S plus 5. Okay. So 2 zeta omega n is equal to 2. Okay. Omega n is equal to root 10. Because if I take 0.5 outside, then this expression will become 10 upon S square plus 2S plus 10. Okay. I have got 2 zeta omega n equal to root 10. From this I can find my zeta is equal to 2 by 2 root 10, which is equal to 1 by root 10. This is the answer. Within this, we also have to find the steady state error. ESS limit s tending to 0 s into ES is equal to limit s tending to 0 s into RS upon 1 plus GS, because this is a unity feedback. HS is automatically 1 tending to 0 s into 1 by s square, because RS is equal to RT is unit ramp, so RS will be 1 by s square, 1 plus 5 upon s into 0.5s plus 1. Limit s tending to 0, 1 upon s plus 5 upon 0.5s plus 1, which is equal to 1 by 5 equal to 0.2. This is the answer for steady state error. Okay. The second part of the same question is, suppose the derivative control system, derivative path is there. Okay. If the derivative path is there, then we have to find the value of Kt and Ka. Write down the statement. Find suitable values of Ka and Kt so that damping ratio of the system is increased to 0.7. Now damping ratio directly they are saying is zeta is equal to 0.7 and without affecting the steady state error. Okay. The steady state error which was found in part first, which is 0.2, it is same, and damping ratio is 0.7 and derivative path has come. So now we have to find the value of Ka and Kt. Solution. Okay. So before finding the other things, we have to find the overall transfer function of the block. Okay. So if we look at the internal block, motor part with feedback, I can have that Ys upon R dash S. Let's assume that R dash S is the input to the motor part. That will be equal to 1 upon S into 0.5S plus 1 plus S Kt, which is equal to 1 upon 0.5 S square plus Kt plus 1 S. Okay. Now when this is a forward when this comes as a forward transfer function with the amplifier, then in that case my Ys upon Rs will become Ka upon 0.5 S square plus S times of 1 plus Kt plus Ka. Okay. The overall transfer function I got is this. Again writing that S into 1 plus Kt plus Ka. I can omit this 0.5, I can write this as 2 times of Ka upon S square plus 2S 1 plus Kt plus 2Ka. Okay. From this my omega n is equal to under root of 2Ka. 2 zeta omega n is written as 2 times of 1 plus Kt, Okay. From this I can write my zeta as 1 plus kt upon under root of 2ka. This is equal to 0.7. So 1 plus kt can be written as 0.7 under root of 2ka. Okay. Now steady state error, I am saying it is same, which is equal to 1 upon s plus ka upon 0.5 s plus 1 plus kt at s equal to 0, which gives me 1 plus kt upon ka. Same it is will be equal to 1 by 5 or 0.2. From this I will get 1 plus kt is equal to ka by 5. Now equating this and this, I can write 0.7 root 2 ka is equal to ka by 5. Okay. Squaring and substituting, I will get my ka is equal to 0.7 into root 2 into 5 whole square, which is equal to 24.5. From this, kt value will be 24.5 minus 1, 24.5 by 5 minus 1, which is equal to 3.9. This way ka and kt value can be found. It is a simple mathematics, nothing more than that. Only thing, just we have to find the overall transfer function, which will be different from the earlier because the derivative path in the feedback loop is there. Okay, so that was the only principle, rest remaining things are same. Next question. A unity feedback system whose open loop transfer function is given. Of course, negative feedback. To s plus 1 upon s plus 1. Okay. Plot Nyquist plot and obtain gain margin and phase margin. So we have to plot a Nyquist plot for this, and also have to obtain gain margin and phase margin. Okay. G of j omega can be written as 1 by j omega 2 of j omega plus 1 j omega plus 1. Okay. So mode of g of j omega at omega equal to 0 is equal to infinity. Angle of g of j omega at omega equal to 0 is equal to minus 90 degree. Okay. G of j omega at omega equal to infinity equal to 0. Angle of g of j omega at omega equal to infinity is minus 90 minus 90 minus 90, which is equal to minus 270. In this case it is minus 90 minus 0 minus 0, which is equal to minus 90 only. So if I draw Nyquist plot, it will be like this. This is minus 90, minus 180, minus 270 and 0, or minus 360 degree. Okay, so we have to find this point, the point at which my g of j omega crosses minus 180 degree point. Okay, net angle g of j omega can be written as minus 90 minus tan inverse 2 omega minus tan inverse omega, which is equal to minus 180 degree when it crosses the minus 180 degree line. Okay, so this will be minus tan inverse 2 omega minus tan inverse omega is equal to minus 90 degree. Okay, so tan inverse 2 omega plus omega upon 1 minus 2 omega square equal to 90 degree. This implies my 1 minus 2 omega square equal to 0, implies omega equal to 1 by root 2, because 3 omega upon 1 minus 2 omega square equal to infinity. So thus omega equal to 1 by root 2. So g of j omega at omega equal to 1 by root 2 is minus 2 by 3. Thus gain margin equal to 20 log 1 by 2 by 3. This is equal to 20 log 3 by 2, 3.52 dB. Okay. Now, this is gain margin. For finding the phase margin, I have to find the unity gain circle, the point at which intersect. Okay, the angle, it is just like this. This point is minus 2 by 3. This is somewhere 1. So when this circle is cutting at some point, so the angle which is making this angle will be my phase margin. Now unity gain circle we can find just by finding the value of omega at which the gain is 1. Mod of j omega equal to 1 at some frequency omega. At that frequency my phase phi is minus 168.6. Thus phase margin is equal to 180 minus 168.6, which is equal to 11.4. So this is the phase margin of this. Okay, from here to here whatever the angle is, I have to subtract that 180 from that. Okay, on subtracting I will get minus 11.4. I have to subtract minus 180 from that. Okay, so this was a typical problem which has appeared in GATE exam 4-5 times. Okay, either we have to find the gain margin or we have to find the phase margin, or now it is appearing as a linked question in which the first part is finding the gain margin, second part is finding the phase margin. Okay, or the first part will be finding the gain crossover frequency and phase crossover frequency, then second part will be finding the corresponding gain margin and phase margin corresponding to the two frequencies which was found in part first. So these were the typical problems appeared in previous GATE exam. One more problem. A characteristic equation is again given. See, the problem can be this problem shows that the problem can be asked in different ways also. Okay. Then for a system, for all the roots of a system to lie in the left half of plane, for all the roots of system to lie in left half plane, the value of A must be. We have to find the value of A, or we have to find the range of A. See, the question is for all the roots of system to lie in left half plane. It can be asked in another way also for a stable system. The value of A is okay, because when the roots of the characteristic equation lies in the left half plane, it means that system is stable system. Okay. Now the solution of this can be found using Routh criteria. Routh-Hurwitz criteria. Okay, so this is SQ, S square, S to the power 0. This is 1 and 4, 3 and A, 12 minus A upon 3, and this is A. So for my this column to be of same sign, my A must be greater than 0 and 12 minus A must be greater than 0. This implies my A must be lesser than 12. Thus, for 0 less than A less than 12, roots lie in the left half of the abscissa plane. Or for these values of A, my system is a stable system. Okay. So this was also the one of the typical problems which can come, and it has already come in the GATE exam. One more problem. A closed loop transfer function is given for a second order system. Okay. Now for this system I have to find the settling time up to 2% stable, 2% final of the final value. When it reaches to that value, find settling time for steady state error up to 2%. Okay. Solution for that. For 2% steady state error, when it reaches to that particular stable value, it requires 4 time constant. Okay. The time constant for second order system is equal to 1 by zeta omega n. Okay. So for 2% my total time will be 4 by zeta omega n. Now omega n is equal to root 9, which is equal to 3 radians per second, to zeta omega n is equal to 4. This implies zeta equal to 4 by 2 into 3 is equal to 2 by 3. Thus settling time Ts equal to 4 into 3 upon 2 into 3, which is equal to 2 seconds. So this is the answer for that. Okay, simple question, but we have to know the formula and the time constant, number of time constant it requires. Suppose it is 5% value, then it is 3 time constant. Okay, but here it has 2%, so it is 4 time constant. For a system to reach the complete 100%, 0% error, it will require infinite time, because that will never happen. Okay. So we'll stop this session. We'll take up another session for the similar problems which has appeared in GATE exam.